Yeah, so thank you again for this recognition. Really humbled. And in today's talk, I will talk about what we have been working on over the last 5 years. Graph neural networks for graph combinatorial optimization. I did not want to make this too technical because I understand that the audience here is comes from a variety of backgrounds, right? So I wanted to share a little bit of what my journey has been and why I chose to work on this problem, and also some of the key ideas and challenges that we discovered during this journey. So I'll start from when I started my PhD, which is 2006. I was really not prepared when I went to PhD right from after finishing my undergraduate education. Did not have much idea about what is research. I went to my advisor and said, please help me out. What should I work on? And then my advisor said, graphs are everywhere around us. Work on graphs. And I realized, oh yeah, I never thought about it. I have read about graphs in my data structures algorithms course, but there are actually so many real world data sets that are modeled as graphs. So for example, if you're using Google Maps, you are doing something on a road network. If you are interacting for example, in Snapchat or Amazon or any of these recommendation engines, you are again interacting with a bipartite graph. Financial transactions, every time you are making UPI transactions or credit card transactions, that is being modeled as a graph, and then there are back-end engines trying to see which one is a fraud account, whether they should give you a call to verify whether you have really made the transaction, or should it be, just let it be, right? And then molecules, materials, protein structure, so many things that are actually real-world graph data. So that kind of excited me. Wow, so many real-world data sets that are modeled as graphs. But what should I do with graphs now? So I started to sort of look into some of the very basic operations. So let's take the simplest operation, which is a similarity search. So let us assume you have a graph database. That graph database could represent, let's say, chemical molecules, and someone gives you a query graph and says, find me all the graphs or all the molecules in your database that is most similar to the query. Or even the simpler, is the query present in the graph database or not? A very simple problem. But turns out this is an actually very hard problem, computationally very, very expensive. Depending on what is the exact query you are solving, this can be NP complete, NP hard, but in general, there are no polynomial time algorithms to actually solve it. Okay. Then let's take another problem, which is again routinely we face in a real world, right? Suppose you have ordered some items from Swiggy or Big Basket, some grocery items, or Amazon needs to deliver the parcel. They need to now figure out, they have a bunch of B items, what is the shortest route through which they can deliver, shortest or quickest route through which they can deliver all the items. Okay. Again, seems very simple, a problem that we routinely need to solve, but this problem again is not something that we can solve in polynomial time. Okay. And then let's take another example, right? Suppose you want to design a viral marketing campaign. Okay, you have some money, you want to hire some influencers in Twitter or Instagram, your favorite social network, and say, go and promote my particular product. Okay, but you can hire only B people because you do not have infinite amount of resources, right? But how do you select these B people so that their tweets reach the maximum amount of people? Okay, something that again that happens. A lot of times in real world today, we hire influencers to sort of promote our products. Again, this is again an NP-complete problem, not something that you can solve in polynomial time. And this is in general, so I started thinking about why are these problems, which seems to be so easy and so easily we can formulate them, why are they so difficult? Now there are many ways you can think about it, but at the core, they are all combinatorial optimization problems. Now what is a combinatorial optimization problems and what makes them hard? So think about building a team, let's say a cricket team that you want to build. You may have lots of good batsmen, okay, but you cannot build a team with 11 batsmen, right? Or if you are building a soccer team, you cannot have all of them who are strikers. And why is that? Because the value of each individual entity in your team, that depends on who else is also there in this particular team. They are not behaving independently, they are talking to each other. Okay, so that makes it a combinatorial optimization problem. And many of these problems that we see here, they have a combinatorial aspect to it, which means that you have lots of options and you are trying to find out what is that particular subset or some of those group of options that comes together as a good solution. And this is what makes many problems on graphs very hard. But then So as in this part of the, I'll dive a little bit deeper. So some amount of technical details will come. So we'll take the similarity search, which seems to be the most simple operation. Why is that hard? We'll take a slightly more detailed look at it. Okay. So what is similarity search here? So let's think about one of the most popular distance functions for graphs. Graph edit distance. Should I use this? Okay. Yeah, so I should use, okay, so let's take graph edit distance, right? So many of us study edit distance for strings in our data structures and algorithms course. It's kind of an extension of the same thing for graphs. So let's say you're given two graphs here, okay? G1 and G2 that we can see over here. And I want to find out what is the distance between these two graphs, okay? Are they similar? Are they different? What is the exact, quantify the similarity and so on. One of the powerful mechanisms of graph distance function is edit distance, which says find the smallest number of edits that can convert graph G1 to graph G2. What edits are allowed? You can remove nodes or edges, or you can insert nodes or edges, or you can substitute node labels or edge labels. And for the sake of simplicity, we'll assume that all edits have a cost of 1. So find the smallest number of edits that can convert one graph to the other. So if for this example, what I can do is I can first do a label substitution. So for example, the label E in G1 gets substituted into label A, and then I can add an edge and then add a node. Okay, that in 3 edits I can convert G1 to G2. A very simple problem. Okay, now how do you actually solve this? How do you find the smallest number of edits that actually does that? So if you now have to solve this, like you have to write program for this, the first thing, given two graphs, the graphs can be of unequal sizes. That's the first thing. So what you do is, first you make the graphs of the same sizes. How do you do that? So take the smaller graph, add some dummy nodes. The dummy node here is shown in this red circle called epsilon. You add some dummy nodes so that they have the same size. And then you construct some mapping from graph 1 to graph 2. Any bijection. Okay, 1-to-1 mapping. And then given this mapping, you can now compute what is the distance with respect to each mapping. And the distance is, if you are mapping 2 nodes of the same label, the distance is 0. But if you are mapping 2 nodes of different labels, then the distance is 1. And the same thing happens for edges. If you are mapping an existing edge to an existing edge, then the distance is 0. And if you are mapping an existing edge to a non-existing edge, right, then the distance is 1. So for this particular case, sorry, it's just moving automatically. For this particular mapping, you can see the distance is again 3. Why? Because I have I have mapped, so I have mapped this, I have inserted an extra node, which is epsilon, and then I have mapped this epsilon to a node labeled E, and I have also mapped a non-existing edge to an existing edge, right? So with a distance of 3, I can convert graph G1 to graph G2. Okay. So now this is just one possible mapping. What is the graph edit distance? The graph edit distance is consider every possible mapping that you can potentially generate, which is n factorial, and then take the distance that is minimum with respect to all the possible mappings. Okay. That is where the challenge comes. N factorial is very, very large. Okay, even if the graph has 20 nodes or 30 nodes, even for small chemical molecules. So this is the challenge, right? How do you solve them? You cannot solve this in polynomial time. This is known to be NP hard, right? But you can go for heuristics. What are heuristics? Heuristics are some rules or ideas that you apply, and in general, these ideas or these rules give you good result. Okay. Now, if you can also bound that this rule will give you a result that is not worse by a certain factor compared to the optimal solution, then you can call it an approximation algorithm. Okay. So sometimes these heuristics may give you approximation guarantee. Sometimes you're just happy with the empirical results that that they give, but there are no worst case guarantees. So if you now think about this problem of graph edit distance, then what could be a good heuristic? Okay. One possible good heuristic could be that I don't consider every n factorial possible mapping. For example, I do not want to map node B to node A. They are different labels. Why do I want to do that, right? I would try to map nodes that have the same label to start with. And then you can also think, I rather would want to map 2 nodes that have the same label and their neighborhoods are also very similar. That is, you have nodes of similar labels in their neighborhood, right? So this is a possible heuristic. So you can actually do that. So one idea is you map two nodes that have the same label and their neighborhoods are similar, right? And this heuristic works reasonably well, right? There, of course, again, you can create those scenarios where they won't work well, but they can be a reasonably, simple heuristic that works well. Let's take one more combinatorial optimization problem, right? Suppose you're in a social network, and in this social network, you have to hire two people to promote your product, okay? Which are those two people that you would like to hire here? One first observation you can make is, I would choose those two people that have very high degree, right? Because if they tweet about it, then a lot of people are going to get their information, right? Which makes, for example, node A have a degree of 3, node B have a degree of 3, and let's say node C, that also has a degree of 3 as very good candidates, node A, B and C. But then look at one more factor, A and B, their neighbors have a high overlap between them. Whereas node C have less overlap with either A or B, right? So this is where the team formation analogy again comes into the picture. A and B are doing similar jobs. They are individually good, but if you make them a team, they are not giving much of a marginal benefit. But if you choose A and C, they are complementary to each other. So I would rather choose A and C, right? Again, a heuristic here. What is that heuristic? Choose people who have high degree and their neighbors have less amount of overlap between them, right? Does that guarantee you the optimal performance? Or no, but it may work in real world, right? I mean, give you decent results, right? So these are heuristics, and heuristics were actually very nice. So I realized this as I was doing my PhD, and I felt, oh, hard problems are nice. I take a hard problem, I show that this problem is not solvable in polynomial time by doing, showing it is NP hard or NP complete, something of that sort, and come up with my own heuristic. Hopefully, we'll think about a problem, the heuristics will work, but I have to generate that heuristic myself and then publish papers, right? This was working very nice for a significant while, and many papers have been published in this particular manner in the data mining and database conferences. But then there was some reality check that I faced in 2018. I went to KDD, I had a paper there, and KDD is sort of the main conference that I consider one of my homes because it's a data mining conference. I was working on data mining. But then I went there in 2018 and I felt that I'm not unable to understand most of the papers. Why? Because almost all the papers were talking about something called graph neural networks, which I just knew something is happening in that space, but I did not really pay much attention to. And what is going on? So one thing I clearly realized that KDD is a place where I have felt this is my main conference and I cannot understand the paper, so I have to fix that. Something has to, have to see what I can do. So this is like that fork, right? I was doing my regular stuff. So the question that I had was, do I continue doing my regular stuff and say, no, my hand-curated heuristics are better, do not go for GNNs, or do I start working into GNNs and then sort of do something on that front? That was the question. But then I realized 2006, I was a graduate student, 2018, I was a faculty by that time, and I had students working with me. So why not do both, right? Send someone for the regular stuff and send some people to do GNNs, right? And that is what we started, right? I mean, we started, so let's do both and then let's figure out which one works out better, right? But then there was another question. Fine, I want to work on GNNs. What do I want to work on? So here's a timeline of some of the very seminal works that happened in GNNs, right? These are the new architectures that appeared, and even today, these are the main architectures that people are going to use if they want to use any graph neural network. So this is 2018. By that time, some of the seminal papers like DeepWalk, which got the Test of Time award in this year's, last year's KDD, Node2Vec, Graph Convolutional Network, Graph Attention Network, Graph Sage, they have already appeared. So there were still, in 2018, when I attended KDD, many people were actually still publishing papers on new graph architectures. But I felt that maybe, the seminal works have been done. If I come up with another graph architecture, graph neural network architecture, it's going to have a marginal impact because the main work has been done. So what do I do? I was still, thinking. So then at that point of time, I was thinking that, okay, so far I have been generating these hand-curated heuristics to solve graph combinatorial problems. Can GNNs actually solve graph combinatorial problems? Okay. Now, this seemed to be an exciting idea. Why? So this is an important, exercise that I do whenever I'm trying to think about any new area or problem that I want to solve. First of all, how many people are working in this space, right? most people were working on graph classification, node classification, link prediction with GNNs, but not really solving graph combinatorial problems, right? So it seemed to be an open space. So if you can do something, there is not too much competition. Second, but why do I want to work on something that is different? What is the potential of that particular work? The potential impact seemed very clear to me. So far, whatever I was doing myself by designing hand-curated heuristics, now if something does it for me automatically by just looking at the data, that seemed to be an exciting idea because, it makes me spend my time doing something else, right? So I don't have to sort of design those heuristics. There will be a neural network that will come up with those heuristics. So that's very interesting. The second part was scalability. The reason is, if you think about neural networks, training is often the most expensive part, but inference is generally fast because you're doing only a single forward pass through your neural network. And then you have GPUs and other kind of, advanced hardware that you can, because most of the otherwise you would be using CPUs for if you write a program, right? You can optimize it with GPUs in some cases, but generally you have to do that extra work. But neural networks inference will happen on GPU, so that speed up comes with it, right? So scalability seemed to be an exciting, impact if we can potentially solve it. And the third part was, what is my idea to solve this particular problem, right? Why would GNNs be good in solving graph combinatorial problems? Now, when I think about it, in general, the heuristics that myself or other people were generating, they typically relied on some frequent patterns or properties of the data set that recurs, right? For example, if you think about the promotion of viral marketing, nodes with high degree and disjoint neighborhoods or not much overlap. That's the core idea, right? If you think about mapping graph alignment, nodes that have similar neighborhoods should be mapped to each other, right? So these are the very core level ideas that works across data sets, right? So if a GNN can pick this up, they should be able to come up with this heuristic. And why should GNNs be able to pick this up? Because it has been shown in many different works that neural networks are good in recognizing frequent patterns. Okay, so that gave me some hope that maybe this is a area that we want to work on. So that was sort of the main reason I went in. So what is the sort of the problem formulation here? So what we are thinking about here is that we are given a training data set of graphs. Let's again think about learning the graph edit distance function, but you can generalize it for anything. You are given a training data set of graph pairs, that ground truth edit distance, and now you want to learn a GNN model that can predict that particular distance well, right? So in other words, you have a GNN you want to train, you are given two graphs, you embed them into some high dimensional space, and then you learn some function automatically, that is what like an MLP or something of that sort, which would learn this function f such that f is almost similar to the true ground truth distance, right? That is the sort of the overall pipeline. Now if you want to do some, not distance, but something else, you have to change the label to that particular data property that you want to sort of learn, right? So now just to quickly, why again? So give you a more fine-grained detail about why GNNs are useful for this. So what does a GNN do? They take a graph and embed every node into a high-dimensional feature space. That is what they are doing, essentially, okay? How does it do that? There are two parts that you need to define. Now, I want to embed them into a feature space such that similar nodes have similar embedding. So if you are thinking in terms of the graph edit distance, nodes that have similar distribution of labels in their neighborhood should have similar embeddings, right? So that is the key idea, right? And that is what the GNNs is. I mean, that's what you have to encode within the GNNs, right? Now, how does a GNN work? So if you take any node, for example, let's say the node A, what node A does is it talks to each of its neighbors and says, give me what is your current value or what is your current representation. Okay. So for example, in the context of chemical compounds, it could be, tell me what is your node label type, what is your atom type. Okay. So A will say, okay, B's atom type is carbon and maybe C's atom type is something else and so on, right? And it will aggregate that information of that neighborhood and represent that in a feature vector. If you're thinking about social networks, it would be, okay, who are my friends? What are their characteristics? Like, where are they from? What is their age? What do they do? And so on. And then I would compute and aggregate information based on that, right? This is what GNNs are good at. And this is exactly what we wanted to also capture when we're talking about mapping between nodes or trying to sort of find out who are good influencers in the social network and so on. And we came up with an architecture for this particular problem, which is in which got published in New 2022. Now, I don't want to go over the architecture, but I want to also mention here that it's not okay. So I'll come to that later. So you have an architecture. Don't worry about the details. If you want the details, you can go into the paper and find it out. So what was the impact, right? So before that, for computing for approximating graph error distance, you cannot compute it optimally because of the NP hardness. The non-neural algorithms, the accuracies are shown over here. So the accuracies here are computed in terms of RMSE, root mean square error. Lower the value, the better it is. Lower means we are closer to the ground truth. And greed is the technique that we came up with, right? And you can see that except one data set, across all the other data sets, the improvement was of course there. And in some data sets, improvement was massive. For example, if you look at the IMDb data set, it's a data set that is very dense. Small number of nodes, but many number of edges. I mean, the errors of some of the based techniques were like in 40s or 50s, whereas we are getting errors in 4.8, right? That's a significant improvement. And it's not just improvement in quality. We are 500 times faster than the good non-neural algorithms. There's also one non-neural algorithm which is very fast, Node, which is a reasonable architecture as well, but Node's quality is not as good as some of the other ones. But the key point here is that you can get massive improvement in inference time while getting good quality. So this was something that happened in 2022. And the similar sort of ideas, this is graph error distance is just one example that we looked at, but we generally, in my group, we started looking at learning graph combinatorial optimization problems using GNNs. And we looked at various different problems, graph cuts, learning distances, graph generative modeling, routing and sensing on road networks and so on. Some of them were very application driven. For example, in graph generative modeling, we tried to sort of design new drugs, design new materials, which are again, combinatorial optimization problems. In the New 2023 paper, we actually tried to sort of distribute sensors in Delhi based on which locations as a whole will give you the most accurate information for doing good interpolation or extrapolation of pollution monitoring, right? So a bunch of different areas where we actually looked into graph combinatorial problems. Now, what is the key message that I want to say? Now, it's not like plug and play. We take a GNN, apply it, and we get the result. No, it is not as simple, right? Of course, you have to customize the GNNs for that particular problem. You have to carefully select the loss function. That is very important to inject the appropriate inductive biases. And how do you model the combinatorial nature, right? The value of every point or every node is not independent of the other one. So how do you model that? There are many ideas you can use, genetic algorithms, reinforcement learning. So we have found reinforcement learning to be fairly, do reasonably well. There are challenges, but it does reasonably well. So we have used it in many of our works. And then there are also questions about what can you guarantee about these techniques, right? These are mostly black boxes. Can you say anything about it, right? So we strive to sort of come up with this kind of theoretical guarantees. What are the key challenges? The first challenge is generating labeled data. Labeled data means ground truth data. That means you are solving the NP hard or NP complete problem that I was talking about. That is our gold standard. So ground truth labeled data is extremely expensive, which means that you cannot get a lot of ground truth labeled data, right? That is the problem. So what are the solutions? One halfway solution I would say is that you can solve the ground truth data on very small instances and then try to extrapolate it to very large instances, right? So that is one option. Or you come up with self-supervised approaches or reinforcement learning based approaches where you don't need any ground truth data. You just evaluate the solution and see how good the solution is and try to improve upon it, right? Second, these techniques we have found to have very poor generalization to distribution shifts, right? You train on one distribution. If the distribution in your production is different, they can fail miserably. So that is one problem, and I don't have a very good solution to it yet. I think this is an ongoing challenge. And the third one is black box, right? I cannot reason about it. Why is it working? Why is it not working? When would it fail? I have no idea, right? So this is the challenges, right, which we have not yet solved. So that takes me to today. What do I want to do? I want to solve the problems that I talked about, right? And how do I do that? So one idea that excites me, again, I don't know how much I can push this because we're just starting in this journey, is from heuristic discovery, where heuristics are just predicted the code. Can we generate the program, that is actual code, that reasons about that heuristic, right? So when I'm generating these hand-curated heuristics in my PhD days, I was writing the program and that program was running, right? I transitioned into something that just predicts the output, but not how the output is being arrived at. So can I generate the program itself, right? That is something that excites me, because it's going to be end-to-end interpretable. I can trace every reasoning to what was a logical decision. It enables human AI collaboration. I can give that program to a human expert and the expert can improve it further. And hopefully I can generate foundational strategies, because code forces you to work at a certain abstraction level and it does not look at distributional aspects as much, right? How? What is my idea now? Again, so it's just an idea at an idea level. So if I look at how neural networks are trained, you typically take a neural network, initialize it with random weights, and then you have some training data, pass the training data, get some predictions, and then you compute the quality of the predictions using some loss function, and you have an optimizer that updates the weights to sort of improve that particular neural network. That is your current pipeline. Now, how can I generate code? So the first change is, instead of starting with a randomly initialized neural network, start with a trivial solution or randomly initialized program, okay? Get the predictions, compute the loss, and then have an LLM agent in between, because LLMs have been shown to do fairly well in code generation, that can improve the code. You tell the LLM that, okay, this is my program, this is the output, can you improve and reason about it and improve it? What are the key challenges here? I mean, I cannot again just plug it an LLM and magically assume that it will work. How do I break down the complex problem into small problems? I think that is very important. Can I do it automatically, or do I have to come in and hand engineer and say, these are the different sub problems to be solved? Of course, I would like it to be automated. How do I prompt? What should be in the prompt that I'm giving to the LLM, right? How do I give it feedback, right? So these are open problems, the research challenges that need to be solved. But what excites me? 5 minutes, I'm almost there. What excites me? So we have one work, it is not published, it is under submission. Hopefully the archive report will be up soon. Going back to graph-weighted distance. So I talked about GREED here, which was a neural network based estimator of graph-weighted distance. And then we have come up with something called GRAIL, which actually gives you a program to compute the graph-weighted distance. And we have been able to, at least on this particular problem, to really outperform anything that exists at the moment. So some of the data sets like Linux and IMDb, we took it from 40s and 50s, the RMSE went down to 4.8 when we came up with a GNN based approximator, and now we have been able to take it down to something like 0.55. So it's a massive improvement that we have been able to see. The details about how the prompt tuning happened, we use a genetic evolution algorithm that we used, and the sub problems we divide up into bipartite matching and so on. So there are many details which hopefully, if you're interested, I'll be able to share with you, and the archive should be up soon, right? But again, we are right now, we started, there was a time when GNN seemed to be the hard path and the regular stuff, the regular hand-curated heuristics seemed to be the easy path. It has changed over the last 5 years. GNN seemed to be the easy one, and everywhere I look, people are working on LLMs, and I'm thinking like, okay, am I missing out on something? I don't know, right? So I don't have a solution, right? Whether LLMs are the best way to go about it, but I have many sort of enthusiastic fork seekers in my group, who are sort of actively working in this space. So I hope again I can sort of use the same sort of strategy and have some people working on LLMs plus GNNs and reasoning, and some people working on pure GNNs, and hopefully we'll figure out in 4 or 5 years, whether I made the right decision or not. So with that, just thank to my sponsors, because this line requires GPUs and LLM API calls, and luckily I have been able to sort of generate funds from many of the industrial partners. So thanks to them, and and that's all. So I'd be happy to take any further questions.
So thank you. First of all, congratulations for your brilliant work. So I have the following question. You give a couple of very good examples of heuristics that human use, okay? So do you think that this machine learning model will come with the new heuristics that nobody has ever thought about, or they will rediscover the human heuristics?
So there is already some evidence that it comes up with heuristics that are better, not better. That's a hard question. On the given training instances, it is coming up with results that are better than what the human generated heuristics have provided on that data set. So the first, or not first, should not say first, the first work that I looked at was something from Google DeepMind. It's called Fun Search. That actually came up with this code discovery, and the heuristics were there. And this work was started as a collaboration with Google by building on top of that. So there is already evidence in the literature where heuristics have been generated that are outperforming human heuristics on given data sets. To say it is always better, that's a broader question to sort. I mean, that's hard to say.
But are those heuristics which are generated by the algorithm something which have a semantic meaning for humans?
So yes, for example, I mean the heuristics that we generated, for example, that were looking at degree, they were looking at clustering coefficients, they were looking basically vertex invariants that remain preserved during graph isomorphism. So they are looking at those kind of features. That does not mean that the program that will work well will always have reasoning that is semantically aligned to you, because we have also seen programs where we say, how is this working well? Because it does not seem to me that it should work well, but it works well. So it happens both ways. But in general, I am positive with my limited experience that most of the programs, they are not completely arbitrary. They do make sense.